When you picture a desert, chances are you're thinking of endless sand dunes. But, these incredibly diverse dry regions actually cover about a quarter of our planet's land surface.
Yeah, they showcase a surprising variety, much more than just sand.
Exactly. So today on the deep dive, we're venturing into the chapter Dry Regions, the Geology of Deserts from Earth, Portrait of a Planet, 6th edition.
Mm-hmm. A great resource.
Our mission really is to unpack the geology here, how these deserts actually form, the unique landscapes they create, the tenacious life they support, and importantly, the impact we humans are having.
And it's not a new fascination. Even way back, people were struck by their stark beauty. Clarence King, the first head of the USGS, he described these bare hills under a pitiless sky. Really captures that essence, doesn't it?
It really does. So prepare to have your understanding of deserts expanded. We'll talk about their intense dryness, those wild temperature swings, and the 5 main categories they generally fall into based on how they form. Subtropical, rain shadow.
That's the mountain blocking moisture one.
Right. Then coastal, linked to cold ocean currents, continental interior basically, far from the sea, and polar deserts.
Yep, covers the main types.
Hmm.
Okay, let's get into it.
So what is a desert, fundamentally?
Well, what's truly foundational isn't just the heat, though that's often part of it. It's the aridity.
Right, the dryness.
Exactly. The chapter formally defines it as an arid region lacking permanent streams unless they start somewhere else, obviously, and with vegetation covering less than, say, 15% of the land.
Okay. And rainfall.
Generally less than 25 centimeters, about 10 inches per year. But, and this is crucial, aridity isn't just about the total amount of rain.
There's more to it.
Yeah, the rate of evaporation is huge.
Yeah.
And also whether that rainfall is, sporadic, like one massive downpour a year or a bit more regular.
That makes sense. A place could get, say, 30 centimeters of rain, but if it all evaporates instantly or falls in one go.
It could still function as a desert, absolutely. That flash flood every decade isn't going to sustain much.
And the chapter draws a useful line between cold and hot deserts, too.
Mm-hmm. Cold deserts stay below roughly 20 degrees Celsius, that's about 68 Fahrenheit, year-round. Think high latitudes, high elevations.
Okay. And hot deserts.
Hot deserts, that's where summer days routinely climb above 35 Celsius or 95 Fahrenheit. Usually lower latitudes, lower elevations. And we're talking serious extremes here.
Like record-breaking heat.
Oh, yeah. Libya apparently hit 58 Celsius once, that's 136 Fahrenheit. And Death Valley wasn't far behind at 57 C. Just scorching.
Wow. And that heat, it must tie back into the aridity, right? Makes evaporation worse.
Precisely. Heat accelerates evaporation significantly. In really hot deserts, rain can sometimes even evaporate before it hits the ground.
Seriously, mid-air evaporation.
It happens. Plus, the intense sun heats the bare ground, creating this superheated layer of air right near the surface. That's what causes those shimmering mirages you see.
Okay. I always wondered about those. But what about nighttime? It gets cold, right?
Drastically cold. That dry air just doesn't hold on to heat. And with no insulating clouds or much vegetation, the temperature can plummet. We're talking maybe an 80 degrees Celsius swing in a single day in some places.
An 80-degree swing? That's unbelievable, from boiling to freezing, basically.
It really underscores the harshness, the lack of moderation.
So how does this extreme environment affect the basic geological processes? Like weathering, erosion?
It changes things quite a bit compared to temperate areas. Without that protective plant cover, the ground is just much more exposed.
Okay, so physical breakdown is easier.
Yes, but interestingly, chemical weathering is generally slower. And you don't get that buildup of organic stuff, humus, in the soil.
Right. So what do you see on the surface, typically?
You're more likely to see exposed bedrock, piles of loose rock bits, unweathered sediment, salt crusts where water evaporated.
And sand, of course.
And windblown sand, definitely. Soils do develop, but they tend to be thinner, more mineral-rich.
And you mentioned caliche earlier, or calcrete.
Yes, that's a key feature. Dissolved stuff, especially calcium carbonate, precipitates out of the water that is there and cements the sediment grains together. It forms this hard, almost rock-like layer just below the surface.
So even in a dry place, you find evidence of past water activity locked in the ground.
Exactly. And the colors you see, like in the painted desert in Arizona, that vibrant color often comes down to the underlying bedrock, specifically variations in iron content and, how oxidized it is.
Okay, that gives us a really good picture of what defines a desert. Now let's dig into those 5 main types based on how they form. First up, subtropical deserts, the big ones.
Right, the big ones. Think the Sahara, the Arabian Kalahari, the Australian deserts. These are huge.
What's the main driver there?
It's fundamentally about global atmospheric circulation, specifically something called the Hadley cell.
Hadley cell. Sounds familiar.
Yeah, near the equator, warm, moist air rises, cools, drops its rain. That's why you have rainforests there.
Makes sense.
But then that now dry air flows towards the poles at high altitude and sinks back down around 30 degrees latitude north and south, the subtropics.
Ah, okay. And sinking air does what?
As it sinks, it warms up and compresses.
Mm-hmm.
And crucially, it actively draws moisture away from the surface. It basically stops clouds from forming, leads to intense sun, high evaporation.
So it's like a permanent high-pressure zone parked there, sucking everything dry?
Pretty much is why those areas are so consistently arid. It's all linked to that large-scale atmospheric pattern.
Fascinating. Okay, next type. Rain shadow deserts. The western U.S. has classic examples, right?
Absolutely. Imagine moist air blowing in from the ocean, hitting a coastal mountain range like the Cascades.
Okay.
The air is forced up, it cools, water condenses, and boom, rain falls on the windward side, the side facing the wind. That's why you get lush forests on the coast.
Right. But what about the other side?
By the time that air mass gets over the mountains to the leeward side, the sheltered side, it's lost most of its moisture. So you get this rain shadow, an area of much lower rainfall.
Creating a desert.
Exactly. Eastern Washington is a perfect example. You go from rainforest west of the Cascades to desert on the east. Really dramatic rainfall differences over short distances, all because of the mountains.
Topography really shaping the climate there. Okay, third type. Coastal deserts near cold ocean currents, like the Atacama. How does cold water make a desert?
It seems counterintuitive, doesn't it? But the key is that cold ocean currents, like the Humboldt Current off South America, cool the air directly above them.
Okay, so the air gets cold.
And cold air is denser. It doesn't want to rise. Often there's warmer air above it, trapping it. This stable, cold layer basically prevents clouds from forming and releasing rain over the nearby land.
So no rising air, no rain clouds.
Precisely, leading to deserts right next to the ocean. The Atacama is the prime example, unbelievably dry. Some parts haven't seen measurable rain for centuries.
Centuries. Wow. Okay, moving inland now. Continental-interior deserts like the Gobi. What's the story there?
Simple distance, really. Air masses pick up moisture over the oceans, but as they travel across huge continents like Asia, they gradually lose that moisture through rain.
So they just run out of water.
Essentially, yeah. By the time the air reaches the deep interior, hundreds or thousands of miles from the sea, it's become extremely dry. It's rained itself out along the journey.
Makes sense, just too far from the source. And finally, polar deserts. Ice and snow, but still deserts.
Yep. Polar regions north of the Arctic Circle, south of the Antarctic Circle get very little precipitation, technically making them arid.
Why so little precipitation?
Two main reasons. First, those global air circulation patterns tend to bring dry air poleward. Second, and perhaps more importantly, cold air simply cannot hold much moisture. Warm air holds much more water vapor than cold air.
Ah, right. So even if it snows, the total amount of water involved is very low.
Exactly. Very low moisture levels overall.
So deserts are definitely not monolithic. They're shaped by these really distinct geographic and atmospheric setups. And the chapter mentions plate tectonics playing a role over the long term.
Absolutely. Continental drift is huge here. Over millions of years, plates move land masses to different latitudes, change their proximity to oceans, build mountains.
Which creates rain shadows.
Exactly. And it can alter ocean currents. The rock record shows places that used to be deserts are now wet, and vice versa. It's all dynamic, thanks to Earth's moving plates.
Okay, so we know why and where deserts form. Now, how do these extreme conditions actually shape the land? Let's talk weathering and soil.
Right. What's interesting is the balance between physical and chemical weathering. Physical weathering is pretty effective in deserts.
Breaking rocks apart.
Yeah. Rocks fracturing along joints, breaking as they tumble down slopes, maybe even shattering from stress. Those big daily temperature swings might also play a role in breaking down isolated rocks.
Okay. But chemical weathering, slower.
Generally slower, yes. It still happens. You get oxidation, hydrolysis, dissolution driven by dew, and the occasional rain. But the lack of consistent water and the low amount of organic acids in the soil means these reactions don't proceed nearly as fast as in wetter climates.
So rocks break apart easily, but don't decompose chemically as quickly. What about desert varnish, that dark coating?
Ah, desert varnish. It's that distinctive, dark, often shiny coating on rocks. For a long time, people thought it was minerals leaking out of the rock.
But that's not the current idea.
No, the prevailing science now suggests it's mostly from windborne dust settling on the rock. Then microbes, bacteria, archaea living on the surface extract elements like iron and manganese from that dust, especially when there's a bit of moisture from dew, and precipitate them as these dark oxides.
So it's an external coating built up over time by microbes.
That's the idea. And because it forms so slowly, maybe only micrometers per thousand years, its thickness can give a rough clue about how long a rock surface has been exposed.
And people used it.
Yeah. Ancient peoples created petroglyphs by chipping away the dark varnish to expose the lighter rock underneath. Art etched into geological time, basically.
That's incredible. A natural canvas. Now back to soil. We mentioned calcrete. How does soil actually develop?
Well, it can form where sediment stays put for a while. Infrequent rains do leach some ions downwards and move fine clay particles. But because there isn't enough water to flush everything out, those dissolved ions, especially calcium carbonate, tend to precipitate lower down, forming those hard cement layers like calcrete.
Got it. And the color? Still linked to the bedrock?
Largely, yes. Without much organic matter to darken it, the soil color is heavily influenced by the iron minerals in the parent rock and how oxidized they are. That's why you get those amazing colorful bands in places like the Painted Desert.
Okay, so water is scarce, but when it does rain, it's a major player in shaping the land.
Oh, absolutely. Don't underestimate water in the desert. Even though rain is infrequent, when it comes, it can be incredibly powerful, especially because there's so little vegetation to hold the soil.
How does it cause erosion?
Even individual raindrops hitting bare ground can splash sediment particles around, starting their journey downhill. Then, if it rains hard enough, the ground gets saturated, and you get sheet wash, a thin layer of water flowing across the surface, carrying loose stuff with it.
And then there are flash floods.
Exactly. Those are the really dramatic events. They happen in ephemeral streams, dry washes, arroyos, wadis, depending on where you are. These channels are usually dry, but a sudden storm can send a torrent of water rushing down.
And that causes intense erosion.
Huge erosion. They can scour bedrock smooth, carve really steep channels, even move massive boulders. It's incredibly powerful, even if short-lived.
And badlands.
Right. In areas with soft, uniform rock or sediment, this water erosion can carve that distinctive badlands topography. Lots of closely spaced parallel gullies and sharp ridges.
A landscape really sculpted by water despite the overall dryness. Okay, let's switch gears to the other major sculptor, wind.
Wind is obviously a big deal in deserts, mainly because there's so little vegetation to block it or hold down the sediment. It gets direct access to the ground.
And it moves sediment like water does.
Sort of, yeah. It carries fine stuff, dust, and silt high up as suspended load. This can travel huge distances.
Like dust storms.
Exactly. Then there's the surface load. This is heavier stuff, mostly sand, that moves closer to the ground by rolling, or, more importantly, bouncing. That bouncing process is called saltation.
Saltation. Okay, explain that.
Basically, wind turbulence lifts a sand grain just off the surface. It travels a short distance in an arc, then hits the ground again, and the impact often kicks other grains into the air. It's like a chain reaction.
And this constant bouncing does things to the sand.
Yeah, it rounds the grains and gives them a sort of frosted appearance from all the collisions. Saltating sand usually stays pretty low, maybe within a meter of the ground, though it can bounce higher off solid rock.
And wind sorts the sediment, too.
Very effectively. Dust goes way up, sand bounces along near the surface, and the bigger stuff, pebbles, cobbles, gets left behind.
Forming. Lag deposit.
Exactly. A lag deposit is that surface layer of coarser gravel left after the wind has blown all the finer material away.
And deflation.
Deflation is when the wind removes so much fine sediment that the actual land surface gets lower over time. You sometimes see shrubs sitting on little pedestals of soil because their roots protected the ground underneath while the surrounding area was eroded away.
And blowouts. Those depressions.
Yeah, blowouts are bowl-shaped depressions scoured out by localized swirling wind vortices.
Okay. We mentioned dust storms, haboobs. They look terrifying.
They can be. Huge walls of dust. Visibility drops to near zero. They can cause damage, disrupt travel. That big one in Phoenix a few years back was a classic example.
And wind doesn't just move stuff. It actively erodes rock through abrasion, like sandblasting.
Precisely. Wind-carrying sand acts like sandpaper. It can polish rock surfaces smooth and carve flat faces or facets onto rocks. A rock shaped by wind abrasion is called a ventifact.
Ventifact, okay.
If the wind direction changes or the rock moves, you can get multiple facets meeting at sharp edges. It's quite distinctive.
And yardangs, those mushroom rocks.
Right. Yardangs form where you have a harder, more resistant rock layer on top of a softer one. The wind erodes the softer base faster, undercutting the caprock, leaving these elongated, streamlined ridges often described as looking like inverted ship hulls, or sometimes mushroom-like if the cap is broad.
And this happens on Mars, too.
Absolutely. Space probes have shown lots of evidence of wind erosion yardangs, ventifacts, dunes actively shaping the Martian surface today. Same basic processes, different planet.
Amazing. Okay, so wind and water are moving all this material around. Where does it end up getting deposited?
Well, gravity plays a direct role with talus. That's just the pile of broken rock fragments that accumulates at the base of a cliff after pieces break off.
Yeah.
Very common in deserts. Often gets that desert varnish coating.
Okay. What about water deposition?
Alluvial fans are a big one. Remember those flash floods coming out of canyons?
Yeah.
When that fast-moving sediment-filled water hits the open plain of the canyon mouth, it spreads out, slows down, and drops its sediment load. It builds up these cone-shaped wedges of sediment radiating outwards.
And they have channels on them.
Right. The water forms a network of shifting channels called distributaries across the fan surface, constantly depositing sediment and reshaping the fan.
And if you have several canyons next to each other.
Then their alluvial fans can merge together along the mountain front, forming a continuous sloping apron of sediment called a bajada.
Bajada. Got it. What about playas and salt lakes? They sound like depositional features.
Definitely. Playas form in desert basins, low-lying areas with no outlet. Temporary lakes might form after heavy rain.
But then they dry up.
Exactly. They evaporate, leaving behind a dry, flat lake bed, the playa often crusted with salts like halite, gypsum, borax that were dissolved in the water. You see features like mud cracks on the surface as the clay dries and shrinks.
And the sliding rocks. Racetrack playa.
The famous sliding rocks in Death Valley. That was a mystery for ages. It turns out, under specific conditions, a thin layer of ice forming overnight, then breaking up, and strong winds, the wind can push these ice sheets, which shove the rocks along, leaving trails in the mud.
Ice in Death Valley, who knew?
It takes a very specific set of conditions. Now, if a basin lake doesn't dry out completely, if it's fed by enough water to be permanent but still has no outlet, the dissolved salts just keep accumulating over time as the water evaporates.
Making it saltier and saltier.
Right, like the Great Salt Lake in Utah. The rivers flowing in are fresh, but the lake itself is super salty because the water leaves only by evaporation, leaving the salts behind.
And sabkas.
Sabkas are specific to coastal deserts in hot regions. They're those flat, muddy, salt-encrusted areas right along the coast, formed by the evaporation of seawater on tidal flats.
Okay. And wind deposition. We know it moves sand and dust.
Right. The fine dust, the suspended load, can be carried way outside the desert and deposited as thick blankets of silt called loess. Very fertile soil, actually.
But the sand stays mostly in the desert.
Yeah, the heavier sand grains transported by saltation tend to accumulate within the desert itself, forming dunes. These can range from small ripples to vast dune fields called ergs, or sand seas, sometimes hundreds of meters thick.
Okay, so we've covered the processes. Let's talk about the resulting landscapes. The chapter stresses variety beyond just sand seas.
Absolutely crucial point. Yes, you have ergs, the big sand seas, but deserts also feature vast rocky plains, areas with sparse vegetation and incredibly intricate rock formations.
Like Hamada and Reg.
Exactly. Those are terms used in the Sahara. Hamada is the rocky, barren highland. Reg is the extensive stony plain, like a gravel desert. And Erg is the sand sea. So, different surfaces.
And overall, desert landscapes look starker, more rugged than, say, the Appalachians.
Definitely. The lack of deep soil and dense vegetation exposes the underlying rock structure much more dramatically. If the Appalachians were a desert, they'd be much sharper, more angular, less rounded, and soil-covered.
Okay, let's look at some specific landforms. Rocky cliffs and mesas seem common.
Very common where you have durable rock layers. The lack of soil cover exposes bedrock ridges and cliffs. Erosion happens as rocks break off along joints.
Leading to cliff retreat.
Right, the cliff face gradually moves back over time, often maintaining a steep profile. This is called scarp retreat. It can happen slowly or in big rock falls.
And the height of the cliff depends on the rock?
Often related to the thickness of the resistant rock layer. And where you have layers of strong rock alternating with weaker rock.
You get steps.
Exactly. Differential erosion. The weak layers erode into gentler slopes. The strong layers form the steep cliffs. Gives you that stair-step look.
And how do you get from a plateau to a mesa to a butte?
It's a progression of erosion.
Yeah.
You start with a large, flat-topped upland, a plateau, defined by a resistant caprock. As erosion eats away at the edges through cliff retreat, it gets broken down into smaller, isolated, flat-topped hills called mesas, which are wider than they are tall.
Okay.
Continued erosion shrinks the mesa until it becomes taller than it is wide. That's a butte. And eventually, even the butte could be worn down into a slender spire or pillar, a chimney.
Like Monument Valley.
Classic example of mesas and buttes. And places like Bryce Canyon show another form, hoodoos. Those are intricate pillars formed by erosion working along joints in layered sedimentary rock, often with wild shapes.
And natural arches.
Arches, like in Arches National Park, form when erosion selectively removes rock along joints or fractures in a fin or wall of rock, eventually punching a hole through it.
Amazing how erosion sculpts these features. What if the rock layers aren't flat but tilted?
Then you get different shapes. If the layers are gently tilted, you form cuestas asymmetrical ridges with a steep scarp slope on one side and a gentler dip slope on the other, following the tilt of the rock layers.
Okay.
If the layers are tilted really steeply, almost vertically, you tend to get narrower, more symmetrical ridges called hogbacks.
Cuestas and hogbacks. Got it. And Inselbergs and pediments, those sound different again.
Inselberg literally means island mountain in German. It's an isolated hill or mountain rising abruptly from a generally flat plain. Think of it as a remnant of a mountain range that's been largely eroded away.
Like Uluru, Ayers Rock.
Uluru is a perfect, world-famous example of an Inselberg, specifically a type called a Bornhart, known for its rounded shape.
And pediments.
Pediments are gently sloping, relatively flat surfaces of bedrock found at the foot of some mountains or Inselbergs in arid regions. They're thought to be formed by erosion, specifically sheet wash abrasion, cutting across the bedrock as the mountain front retreats. They're often covered by a thin layer of gravel.
So remnants of erosion. What about stony plains and desert pavement?
Stony plains are just those widespread lowland areas covered in gravel, the lag deposit we mentioned. Desert pavement is more specialized. It's that incredibly smooth, tight mosaic of closely fitted, often varnished stones covering a layer of finer silt and clay.
How does that form? It looks so constructed.
Yeah, the mechanism's debated. The old idea was purely lag deposit, wind blows fines away, leave stones. But newer ideas suggest fines might filter down between the stones, and then cycles of wetting, drying, or frost heave slowly push the stones upwards and jostle them into that tight fit over long periods.
Interesting. Still some mystery there.
A bit, yeah. But whatever the exact process, they're remarkably stable surfaces, yet very easily disturbed by things like vehicles.
Right. Fragile despite looking tough. Okay, finally, let's get to the classic image. Seas of sand. Dunes.
The ergs. Yeah, dunes are basically asymmetrical mounds or ridges of loose sand piled up by the wind.
How do they start?
Usually, sand starts to accumulate behind some kind of obstacle, a rock, a bush.
Yeah.
Once a small pile forms, it creates its own obstacle, influencing the airflow and causing more sand depositions, especially on the downwind side.
And they move.
Definitely. Sand saltates up the gentler windward slope.
The bouncing process.
Right. Then it reaches the crest and avalanches down the steeper leeward side, called the slip face. The slip face maintains a constant angle, the angle of repose for sand, typically around 34 degrees. This continuous process makes the whole dune migrate downwind.
And leaves behind patterns inside.
Yes. Those buried slip faces create crossbeds, layers inclined relative to the main dune structure, which geologists can use to figure out ancient wind directions from fossilized dunes.
Clever. And the different shapes, barchans, star dunes.
The shape depends mainly on sand supply and wind conditions. Barchans are the crescent-shaped ones, tips pointing downwind. They form with limited sand and steady, one-directional wind.
Okay.
Star dunes are complex, with multiple arms radiating out. They form where wind comes from several different directions.
Makes sense.
Transverse dunes look like waves, long ridges perpendicular to the wind. They need lots of sand and moderate, steady winds.
Like sand waves.
Pretty much. Parabolic dunes are U-shaped, but their arms point upwind. They often form where vegetation anchors the arms and strong winds blow out the middle, or when strong winds break through transverse dunes.
Okay, arms point the other way.
And finally, longitudinal dunes, or seif dunes, are long, straight ridges parallel to the prevailing strong wind. They form with abundant sand and strong, consistent winds, like in the Rub al-Khali, the empty quarter of Arabia.
Amazing variety from just wind and sand.
Yeah.
They can move significantly.
Oh yes, dunes can migrate meters per year sometimes. But they can also be stabilized if vegetation takes hold, like in the Nebraska sandhills, which are ancient dunes now covered in grass.
So even deserts aren't static. Now, life. It seems impossible, but things do live there.
Absolutely. Life finds a way.
Huh.
Plants and animals have evolved incredible adaptations to deal with the heat and the lack of water.
Like what for plants?
All sorts of strategies. Some have seeds with tough coats that wait years for enough rain, then germinate super fast. Others have incredibly deep taproots to reach groundwater, or wide, shallow roots to grab any surface moisture quickly.
And succulents, like cacti.
Yep, succulents store water in fleshy stems or leaves. And many desert plants have spines or thorns, not just for protection, but also to reduce water loss and maybe even provide a bit of shade.
Clever. And oases, they're like biodiversity hotspots.
Exactly. Oases are where groundwater comes to the surface, creating these islands of green with much more concentrated life than the surrounding desert.
And the animals, how do they cope?
Lots of ways. Some, like desert frogs, might go dormant underground for months or years waiting for rain. Reptiles often bask to warm up, but seek shade or burrows during the hottest part of the day.
Nocturnal activity must be common.
Very common for mammals. Avoid the daytime heat altogether. Think of kit foxes or many rodents. Some animals, like jackrabbits or fennec foxes, have huge ears packed with blood vessels to radiate heat away.
Natural radiators.
Pretty much. And physiologically, many have incredibly efficient kidneys to conserve water, producing very concentrated urine, and they lose very little water through sweat or respiration. Camels are famous for this.
So it's a whole suite of adaptations allowing life to persist. But the chapter ends on a more sobering note, the problems humans create or exacerbate in deserts.
Yeah, that's a critical part of the story. While people have lived in deserts for millennia, often nomadically, the modern push of large populations into arid regions brings major challenges.
Water is the big one, I assume.
Huge. Growing cities pump enormous amounts of groundwater faster than it's replenished. This drops water tables, dries up springs and rivers.
Causing land to sink.
Yes, land subsidence and cracking can happen. Native vegetation dies off. Plus, introducing non-native species can wreck the existing ecological balance. But the overarching issue is often desertification.
Desertification, turning non-desert land into desert. How does that happen?
It's often a combination of natural drought cycles being made much worse by human activities. Things like overpopulation, putting pressure on resources, overgrazing by livestock stripping vegetation.
Careless farming.
Yeah, agricultural practices that deplete soil moisture and nutrients, remove plant cover, making the soil vulnerable, and diverting river water for irrigation upstream can starve downstream areas.
The Sahel region in Africa is a major example in the chapter, right?
A tragic example. Historically, it supported vegetation and pastoralism,
Yeah.
but a combination of drought, population pressure, overgrazing, and farming changes led to massive soil erosion by wind, loss of productivity, famine, and displacement.
Devastating. And the Aral Sea.
Another stark case. Once the fourth largest lake in the world, it shrank dramatically because the rivers feeding it were massively diverted for Soviet cotton irrigation projects. Huge environmental and human health consequences.
It's not just elsewhere, though. The U.S. had the Dust Bowl.
Absolutely. The 1930s Dust Bowl on the Great Plains was a classic case of natural drought combined with unsustainable farming, plowing up native grasslands whose roots held the soil together. When the drought hit, the topsoil just blew away in massive dust storms.
Leading to huge hardship and migration, the grapes of wrath.
Exactly. And even recently, the California drought from 2011 to 2017 showed the vulnerability of even developed regions to prolonged water scarcity, impacting agriculture, water supplies, and increasing wildfire risk. It wasn't permanent desertification because the rains eventually returned, but it highlighted the stress.
And climate change could make things worse, potentially turning farmland into desert.
That's a major concern. The chapter mentions the Fertile Crescent in the Middle East, which was wetter in the past. Climate shifts can dramatically alter landscapes over long timescales, and current global warming trends could push some semi-arid agricultural areas towards desert conditions.
And one last concerning point, blowing dust carrying pollutants, pathogens.
Yeah, this is an emerging area of concern. As deserts expand or as stable desert surfaces are disturbed, more dust gets into the atmosphere. If this dust comes from former agricultural lands, it can carry residues of pesticides, herbicides,
And microbes.
and fungi bacteria. This dust can travel thousands of miles. Saharan dust regularly reaches the Caribbean and the Americas, potentially carrying chemicals and microbes across oceans. It connects ecosystems in unexpected and sometimes worrying ways.
That's a sobering thought, local land degradation having potentially global impacts. Okay, so let's try to wrap this up. Key takeaways from this deep dive into desert geology.
Well, I think number one is diversity. Deserts aren't just sand. They're incredibly varied environments.
Right, and they're shaped by unique processes, weathering, erosion, deposition driven by wind, and that's surprisingly powerful, though infrequent, water.
And different types, subtropical, rain shadow, coastal, interior, polar form. due to very specific geographic and climatic controls.
We also saw how life adapts in really remarkable ways to survive those extremes.
But also, critically, how human activities can really disrupt these systems,
Hmm.
leading to desertification, which has serious consequences, not just locally, but potentially globally, through things like dust transport.
It definitely leaves us with a lot to think about. Which brings us to a final thought for you, the listener, to chew on.
Given everything we've discussed, the increasing pressures from climate change, growing populations pushing into arid lands, what do you think are the most critical, the most essential strategies we need to focus on? How can we mitigate desertification and manage water more sustainably in these dry and semi-dry regions around the world?
That's a huge and vital question. Definitely something worth pondering. And if you want to explore these landscapes visually, the chapter we used, Dry Regions, The Geology of Deserts from Earth, Portrait of a Planet, has an excellent GeoTours worksheet and online resources. We really recommend checking those out.
They really help bring the concepts to life. And just to confirm for everyone listening, we have made our way through the entire chapter for this deep dive. We've hit the core geology ideas, the key processes like weathering, erosion, deposition.
Talked about the diagrams, the GeoTours examples, linking ideas to real places.
Exactly. Covered the hands-on applications, tried to explain the terms clearly, and hopefully related it all back to real-world sites and issues.
I think we covered it all. Thanks for joining us on the deep dive.